Okay, let's review what we did with the Incline Plane Lab. And so here was a table, and here was we inclined with the whiteboard this little toy car at different angles, and these were the angles that we used, you know, of how much angle of incline. And then you measured this, and then you graphed it. Right? Now, so, and our question was, well, what kind of shape is this right here? And we had a lot of different suggestions. This kind of looks, maybe it's an exponential function. Maybe it looks kind of like a sine wave. Maybe it's a parabola. You know, it could be a lot, you know. So you look at data and you go, okay, there's something going on here. What is it? Then we just watched the lecture of inclined planes. And what we said was, well, let's draw a free body diagram of this car now. And so here's our little toy car. And we pulled on it like this. I'll call this the applied force. We applied a force to it to keep the car from accelerating down the incline. In the meantime, gravity is pulling straight down. That's m times g. And then we've got the wheels. Now the wheels, there's no friction in this problem. The wheels keep the friction from happening. So this is going to be straight up like this. And so this is the normal force. And I'm going to call up the incline the x direction. Perpendicular to the incline, that's going to be my y direction. So this is what we did in the thing. And I'm just following the procedure here, right? Well, now I got to break up this weight force into its components. Well, here's the component that's perpendicular to the incline, the y component of the weight. And since this is my angle of incline, if this is theta, then this is theta. Well, this is the adjacent leg, so it's the hypotenuse, mg, times the cosine of the angle. And then here is the parallel component of the weight, mg sine theta. It's the part of the weight that's pulling it down the incline. Now, if we sum the forces in the x direction, it should be equal to ma in the x direction. Right, we're doing step 4 of the procedure now. Well, look at the free body diagram. Let's look in the x direction. What forces are acting in the x direction? Well, I'm pulling it in the x direction, so that's Fa. Now, the normal force is not in the x direction. It's not part of the equation. Neither is mg cosine theta, but look at mg sine theta. It's in the negative x direction. Does that make sense? So we're going to say minus mg sine theta. Don't freak out because sine is in the x direction. It's all based on where we define the angle to be in the right triangle. That's what determines what is sine and cosine, the right triangle, and the definition for sine and cosine. Equals, now was this little car accelerating? Was there any acceleration in this problem? Well, a couple of you dropped the cars on the floor, but other than that, no, there was no acceleration. So that's equal to 0. So what does this tell us? Oh, hey, the applied force should be equal to the weight times the sine of the angle. This is a theoretical prediction. I didn't take any data for this. I just used Newton's second law, merely a theory. And out pops this little equation. Hey, the applied force to hold that car in place, if there's no friction, should be equal to the weight of the car, m times g, times the sine of the angle of incline. Well, look at this. Does this look over here? Does this look like a sine wave? Kind of. Now, here's what I would like. Who's got a nice, neat notebook? Somebody in the front. Please don't make me get up. Does somebody have their graph drawn, have their data and their graph drawn, I'd like to use your notebook. You. Grace. That's right, Grace. Yeah, I saw Grace's notebook earlier, and I knew it looked pretty good. So here's Grace's graph. Look how, so good. All right, so it kind of goes like this, and then it kind of starts swooping over. So what we're going to say, we're going to use her data. Now you can use your own data. Please use your own data. Now, the theory says that her data, that the applied force, let me zoom in. She writes smaller than I do. Let's zoom in. The applied force should be equal to mg sine theta. So what if I graph the applied force as a function of the sine of the angle? We've never done this before in this class, so really listen. And they want you to do this sort of thing on the AP test, so really listen. This is very cool. I'm going to make a new, I'm going to make a new data table. I'm going to add to your data table. I'm going to go sine theta. I'll try to make my handwriting nice and neat so as not to. Okay. I'm going to get my calculator out. What's the sine of 0 degrees? 0. Don't need a calculator for that. What's the sine of 15 degrees? Well, the sine of 15 degrees is 0.258 or 0.26. What's the sine of 30 degrees? 0.5. I don't even need the calculator for that one. What's the sine of 45 degrees? Root 2 over 2 or 0.707. Right? I want decimals now. What's the sine of 60 degrees? I know this one. 0.866 or 0.87 actually. 75, I don't know that one. 75, oops. Sine of point, what is the matter with me? I'm trying to go too fast. That's what's wrong with me. 75 degrees. 0.96. Actually, 0.965. I'll go ahead and include that. And then 90 degrees is 1. Now, here's what I want you to do. I want you to graph, let's draw another graph. Let's graph the applied force as a function of the sine of the angle. Okay, so let me zoom out a little bit here so we can see. Well, I'm going to do it. And if the bell rings when I'm doing this, just, you can leave quietly, but I want to finish this. Sine of 0 goes from 0 to 1. So I'm going to go 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. So this is sine theta. It doesn't have any units. Off screen? Okay, I'll fix that. And then this is going to be our applied force in newtons. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, zero force. 0.26, where is 0.26? 0.26 is right about here. And then 2, 4, 6, 8. Shouldn't have talked about my car so much, huh? 2 newtons, is that right? And then at 0.5, what was it? 4.5? Oh, look at this. And then at 0.707, here's 0.7, a little bit bigger, so kind of in there. It's 6.8. Here's 7, 6.8 to be right about here. And then 0.866. Be right about here. What was the force? 8.5. 8. Here's 8.5, right about there. And then now we've got 1 is at 9.6. And look at that. It makes a beautiful straight line. Now remember, y equals mx plus b. Well, here our y is the applied force equals the slope. Calculate the slope of this. And then what is the horizontal axis? Sine theta. And then your b is 0. Guess what this slope is? Well, you're rising 9.6 newtons over 1. That's a slope of 9.6 newtons. Guess what the 9.6 newtons is? That's the weight. So we can say that the applied force equals mg sine theta. We got that from the data. Ooh, that was a little rap. mg sine theta from the data and from theory, they agree perfectly. This technique is called linearizing the data. If you think you know what the mathematical relationship is, graph your vertical data as a function of the function you think it should be. If it comes out to be a straight line, you nailed it. You guessed right. So now, well, we're going to end it there because the bell's about to ring. So that is all.